considered to be organic. So NaCN, CaCO3, those are inorganic compounds. Anything else that contains carbon is considered to be organic, like propane, methane, octane, methanol, ethanol. Yes, they contain other things, but the fact that they contain carbon is the defining feature where we put them into the organic compounds. We could look at the carbon-containing compounds in the body. This being Alberta, we're going to look at some of the organic compounds contained in petrochemicals. So just briefly talking about petrochemicals, there's a bunch of different things that we pull out of the ground in Alberta. I don't know what I made you write down, but natural gas, that's probably the leading thing that we're going to be exploring for in this area. Coal-based methane is more along the mountains where there's coal, down by Hinton, etc. Crude oil, there is a lot of crude oil up around near west of Manning in our area. Heavy oil is our oil sands. Well, heavy oil is the oil sands project near Peace River. The bitumen or oil sands is the process in Fort McMurray. But they're all made up of innumerable carbon-containing compounds. Everything from C4H10 to C25H52 and larger when we start to pull out the oil sand stuff. We're not going to spend a huge amount of time on all these different ones. There's a bit or a map on the next page, just give you an idea where they're coming from. Obviously the exploration, the processing of these compounds are what's driving Alberta's economy at the moment. And unfortunately, we don't control the price of gasoline. That's the people in Saudi Arabia and this area. The thing is, 75% of what we pull out of the ground, from crude oil down to oil sands, goes into, actually, I think it's about 95% goes into powering vehicles. We use natural gas for heating our house. We would use coal-bed methane for the same thing. We would also use that for powering some vehicles, not so much in Alberta, but they do use it down south. Basic, you can see we've got our oil sands, which does extend into the Peace River area, probably even a little bit north of us. We've got lots of natural gas across the province. You can see it in our area here. We have conventional crude oil, a little bit up here. And then there's coal along the mountains here, which it doesn't say, although to me, coal is Coal is essentially a dead industry, I would hope. It is so dirty. Not that oil sands are much better, neither is conventional crude oil. It is relatively dirty. The cleanest of these in terms of creating the amount of carbon and other pollutants that go into the atmosphere is natural gas. Now we're going to look at those compounds that make up. But let's take a kind of a U-turn and talk about structural diagrams. I briefly mentioned this in grade 11, probably even less, more briefly than I normally would. We have what are called molecular compounds, and we have what are called structural compounds, and there are structural diagrams also. Okay, for the reason why in ionic compounds we say, okay, there's one oxygen for every, one oxygen for every beryllium if they're together, or one calcium for every carbonate ion. There's millions of them, but there's one for one. That's not the case when we start to talk about organic chemistry. Example, C2H2 and C6H6 both have a formula unit, i.e. if you reduce them down far enough, you end up with one C and one H. You do not want to mix these compounds up. Used in welding extensively, carcinogenic compound that we really don't want around us, as in by itself. So a structural diagram or a structural formula is going to be used. Now, we also have, these are what are called molecular formulas. Now, a molecular formula gives exactly how many of each atom are in the molecule. Okay? So, C2H2. Doesn't give you any structure, but it does give you what's there. Same thing with the C6H6. Okay? So, molecular formula, we could have a structural formula. That would be a, I'll just might write it a little bit differently. This is the structural formula for H or C2H2. You have two C's bonded onto each other and two H's on the end. The structural formula for that one I don't actually have because I use a structural diagram for it. Okay. So a normal structural formula shows everything. Now, and you're going to be able to develop this. How many bonds can carbon form? Well, carbon is in the 14th column there. It has 4 valence electrons. It can form 4 bonds. Here we have C5H12. And I'll show you how I develop this later on. This is a full structural formula. All C's, all H's, each bond indicated with a dash or a line like that. Now, this here is a structural formula. This gives me a hint on how it's structured. And you guys have to remember how that works. Here I've got 2 C's with 5 H's surrounding it. Then I have another C, and this is where we'll develop this. That COOH means I have a double bonded O off the top of the C. And then I have an O and an H. Again, I did talk about it briefly last year. I know with the destruction, you probably don't have a huge amount of memory of that. Okay. So those are our structural formulas. It is a diagram, a 2-dimensional representation, how a 3-dimensional object might look. Okay. Personally, I'm lazy. And I'm sure other people do this. I call this a Hobie structural diagram. I'm sure other people do it. I'm not the first. I just don't write the H's. I have all the C's, everything else, and I don't write the H's if it's a carbon-hydrogen bond. So it's the exact same thing as above with the H's left off. And this one would look like that. Because this is not a carbon-hydrogen bond, I do put the O or the H on. Okay, so those are our basics. Okay. There are also condensed structural diagrams. Right? A condensed structural diagrams, basically what we have here, you can also do a condensed structural formulas without the line. We have a CH3 followed by a CH2, followed by a CH2, and so forth, followed by a CH3. So what I've done from this back one is I have three hydrogens off this carbon. Instead of writing the bonds, I just put them next to it. Now, a condensed structural formula will be exactly like that, except without the bonds. So there would be a condensed structural formula for that. For the propanoic acid, okay, and that's what you're going to see for a condensed structural diagram. Again, oh, sorry, that's a formula. I'll just put my dashes in there. Now, in this case, that's COOH. We are going to have to memorize what that COOH tells me in terms of structure. We'll spend more time on this later, but it does, that COOH looks like this. Now, both of those, the last two are for the slightly lazy person. No, I'm the other one. But because sometimes we start to draw compounds that contain 20, 30, 40, 50 carbons, they've made it even more compact. A line structural diagram shows the carbons as lines, hydrogens as nothing, and then everything else we do have to put in. So we have 5 carbons in a row. That line represents that carbon and that carbon. There's a carbon at the end of that line, there's a carbon at the end of that line. I have 5 carbons. That is actually the structure for C5H12. You have carbon has 4 bonds. There's 4 bonds that carbon can fill. So that means I've got 1 bond filled with a carbon-carbon bond, 1, 2, 3 filled with a hydrogen. 2 bonds off this carbon are filled with a carbon-carbon bond. There's 1, 2 hydrogens there. 1, 2 hydrogens there, 1, 2 hydrogens there, and 3 off the back. The line structural diagram at the end of each line represents 1 carbon, and since there's nothing else there, we don't write the hydrogen, we just know that it's filled. Carbon has to have 4 bonds. So there's only 1 line, 3 of those bonds have to be filled with hydrogen. This one here, 1, 2, 3 carbons. We have a double bonded O off of the 3rd carbon. We have another O. That's bonded on, but it means it's bonded onto an O, and then we'll put the H in quite often there. Okay. I like them because they're shorthand, but you really have to squint hard to see what the amount is. How many carbons, how many hydrogens, etc. So C2H4, we're going to go through each of them. A complete structural diagram, you have 2 C's, I have 4 H's. Now, sometimes we have to think about this. Oh, that don't make sense. I have only 2 bonds filled with this carbon. That's kind of annoying. I only have 3 bonds filled with each of those carbons. How do you think I fill the 4th bond? I'm going to create a double bond between the carbons. To get 4 bonds for each carbon, I needed to have a double bond with it. So there is your complete structural diagram. The condensed structural diagram would be CH2, CH2. Because it's a diagram, it's got those 2 bonds. A condensed structural formula doesn't have the bonds in it, so it would just be CH2, CH2. Difference between formula and diagram, we don't write the bonds in the diagram. The line structural diagram, there's 2 carbons. I have a double bond. We know we have a double bond because we created it up there. And that is all I'm going to write for C2H2. There's a carbon on this end, there's a carbon on that end, and those 2 carbons are filled. What's the remaining 2 bonds that it has are going to be filled with hydrogen. Essentially, we're not writing down hydrogens or carbons. We are writing out everything else. C6H14. This is why I'm not a big fan of full structural diagram. 6 carbons. If I put a hydrogen on every carbon, I end up with 14 hydrogen. And this is why I get tired of putting hydrogens on. Very seldom am I going to actually write out that entire thing as a full. I'll leave the hydrogens off. I will have to put every bond there, but I'll just leave the hydrogens off. The condensed structural formula, the first guy has a CH3, carbon with 3 C's off of it, onto a carbon with 2 H's, a carbon with 2 H's, and so forth. Yeah, the condensed structural formula wouldn't have the dashes between. The reason I don't like the condensed structural formula as much is when we start to talk about double and triple bonds, where are they located? We have to hunt for hydrogens to figure that out. It's much easier just if it's written like this. A line structural diagram is just 6 carbons in a row. So I have 6 endpoints. 1, 2, 3, 4, 5, 6. Now, if someone was neater than I am, we wouldn't have that. They would all be the same size and nice and neat. CH3OH. This is a condensed structural formula because it gives us a hint on the O and the H. We have a carbon with 3 H's and the OH. A condensed structural formula would be a CH3OH. The line structural diagram is going to look, you have 1 carbon bonded onto an oxygen. So that's not a carbon. That's bonded onto an oxygen, and then I'll go my H here. What's the smallest line diagram I can make? What's the smallest number of carbons I can make a line diagram with? 2. And I can't make CH4. I'd probably just use right at CH4. Any concerns or comments with these? Okay, another kind of a U-turn. Hydrocarbons. Definition of a hydrocarbon. A compound containing only carbon and hydrogen. That is it. It contains an oxygen, not a hydrocarbon. It's a hydrocarbon derivative, but not a hydrocarbon. Can be a hydrocarbon derivative. We do have 4 classifications for them. We'll discuss these classifications as we go on. The one that we're going to talk about today is alkanes. One of the issues with organic chemistry is not a spoken language. You really have to be careful to listen to when I say alkanes, alkenes, alkynes. They sound an awful lot alike. The written language, it's a lot easier to see it. And alkanes have only carbons and hydrogens and only single carbon-carbon bonds. They all break down to this formula called the formula unit. It has N carbons, twice as many plus 2 hydrogens. So if I say C24H50, okay, double my 24 to get to 48 plus 2. I know that that compound is an alkane and therefore has only single bonds. Examples: methane, ethane, octane, and then C25H52, which I don't know the names for it. I know there's something out there, I just don't know the name. Okay, we are going to ask to name up to 10 carbons in length for parent chain. A word here, a homologous series. It is a sequence of molecules similar in structure, but only different in the number of repeating units. Okay, so that word homologous, that's what it means. It's in the same, it has the same basic ideas, but it has one extra or one less than the next guy. These are all homologous with each other. They are all in the alkane series because they only contain single carbon-carbon bonds and 2 extra hydrogens. So CH4, there's my lazy diagram. C2H6 and C5H12. And once you look at those diagrams, you can see where the CnH2n plus 2. Each carbon consists of 1 C, 2 H's, and then your N carbons have an extra 2H, or an extra H off of each one. So CH2, 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 CH2 plus 1 hydrogen plus another hydrogen. Now, these are called saturated hydrocarbons because they have all of their bonds filled. In this case, it's called a saturated hydrocarbon because all of the bonds are filled either with carbon-carbon bonds or with carbon-hydrogen bonds. Putting a double bond in there makes this an unsaturated hydrocarbon because it has more space to put more hydrogen. Okay, so that terminology, saturated hydrocarbon or saturated compound, is going to be important. An isomer, by definition, a compound that contains the same number of atoms, same type of atoms, but have a different structure. I've given you an example there. We have butane and then an isomer of butane called methylpropane. These compounds have very similar chemical and physical properties, but not exact. Okay? Boiling point is a really good example. The boiling point of butane and the boiling point of methylpropane are different. This guy, butane, has a higher boiling point. Now we can explain this, and I'm going to spend a lot of time on this unit going over our Intermolecular forces, I'm probably going to have to do a lesson in there that I haven't prepared because we didn't cover it that well last year. Butane has a higher boiling point because butane can get more tightly packed with each other. The closer they are, the stronger the forces are. It's like in any electrostatics. These guys can't get quite as tightly packed together because there's this branch coming off that'll kind of stops all the carbons from getting close to each other. Hence why methylpropane has a lower boiling point. They can't get as close to each other, therefore the forces holding them together are not quite as high. Problem is, why did I call that methylpropane? Okay, well that's what we're going to explain. That the ability to name isomers is very important. They are both in the category of butane. They both have 4 carbons and 4 carbons and 10 hydrogens. 4 carbons and 10 hydrogens. But this guy's got a slightly different. How do we name him? The nice thing about organic chemistry is they start with a principle and they tweak that principle to as we go and get more interesting compounds. We don't end up worrying, we're going to name this way and then we're going to name that a completely different way. We're going to start with the basics and we're going to add to the basics throughout. We're going to start with these prefixes. Now there are prefixes for 11, 12, 20, 30, and I'm sure there's prefixes for other ones. I only know 11 or up to 11 and 12 and don't know any past that. So if you have 1 carbon in a compound, we use the prefix meth. No, not meth, the drug, although it may probably have some type of dealing with that. If they have 2, we use F, 3 prop, 4 but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. Just like we have with geometric figures, starting with 3, we go triangle, quadrilateral, pentagon, hexagon, septagon, or heptagon. The number of carbons in this case is going to deal with the prefix. Because we're dealing with alkanes, the suffix is ane. Now, we're going to talk about alkenes, which has double bonds, and I'm going to name something methene. No, I'm not methene, but I can do fe and fine for triple bonds. As I said, it's not a great spoken language because you have to really hear, and I have to really emphasize those suffixes. So keep these in mind. Now, what's 11? Anybody know what an 11-sided figure is? Undecagon, and a 12-sided figure is a dodecagon. We have the same thing here. Undecane is 11 carbon, has 11 or an alkane that has 11 carbons, and a dodecane or dodecane is something that has 12 carbons and all the hydrogens it needs. That's our basics. This does not change. If I start to talk about organic acids, an organic acid that has 1 carbon in it is called methanoic acid. If it has 9, it is called nonanoic acid. So we're changing the suffix, but the prefix tells you how many carbons are there. That's for our basics. Now each of these from here down has many isomers. Dodecane, I don't know, I can't count how many that dodecane or decane has in terms of isomers. There's a lot. How do we name the isomers? Okay, fairly simple. People have said to me, well, why is this so complicated? Well, it's complicated now because it stays the same throughout what we're going to do. We are going to find the longest chain of carbons.
and we're going to number it. I'm going to number it, in this case, from left to right. Now, I won't always number it from left to right, because I want to number it so my branch comes off the lowest carbon. I'm going to tweak that when I have double bonds and triple bonds and other things, but I want my branch to come off my lowest carbon. So going back to what we talked about, what's the prefix for a 5-carbon chain? Rory, you're looking right at it.
Pentane. What about the bottom carbon?
We'll get to him in a minute. So the parent chain, the longest chain, which we call the parent chain, is called pentane. And then I'm going to name the branch. This is an isomer of hexane, because it has 6 carbons. We know it's an isomer of hexane because it has 6 carbons. It has a different name than hexane, though. We are going to call this branch here, has 1 carbon in it. So we're going to use the prefix meth. And to indicate that it's a branch, we put the suffix YL. Methyl means it's the branch of. Now, there's a couple places I could put that methyl branch on this parent chain, 2 of them actually. So I'm going to call this 2-methyl pentane. There's another one. Here's the other one that we could talk about. And this is why we have to call it 2-methyl pentane. This is still, parent chain is still pentane, but I have to call it 3-methyl pentane. Why? Because that tells 3-methyl, my carbon is coming off my 3rd carbon. Doesn't matter which way I number it, 1, 2, 3. So the number tells you which carbon it comes off of. The prefix tells you how many carbons in the branch or chain. Okay. Is there such a thing as 1-methyl pentane? No. Even if it looks like this. Okay, this is not 1-methyl pentane because the longest chain is 6. This is just called hexane. I don't care if the thing is bent. If you can trace the number of carbons with your pen, that's your long, without lifting your pen, that's your chain, your parent chain. This one down here. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. And I deliberately started numbering it from the far side. If I had started numbering it from this side, don't worry about putting these numbers in. What did I miss? Oh. There we go. The blue numbers, notice what happens if I start numbering it that way. We're still going to have nonane. That's our parent chain. In red, my first branch comes off 4, so I have a branch that's 4, 5. If I number it in blue, it comes off 5, 6. We want to number so our branches are off the lowest possible carbon. I will tweak that where we start adding double bonds. Double bonds are more important than branches. So the proper name for this is going to be 4 ethyl, 5 methyl, nonane. There's a reason, even there was a reason that I put it in here. Ethyl is first in the alphabet, E is before M. So I don't care what the numbers in front of it are. It could be 5 ethyl, 4 methyl, not in this case, but it could be. The ethyl comes first because the convention is keep it in alphabetical order when naming branches. So again, this idea of, here's our process. Keep it simple. Alphabetical order is simple. Most of us should know how to do it. Although I still have to rattle them off when I get to about N. I have to figure out which one's which sometimes. So naming these isomers. Okay. Looking at this guy, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. I do look at everything. Our longest chain in this case is the straight one. But I do check to see if there's others. So the parent chain of this guy is pentane. I do have it numbered wrong though. Okay. I would have a branch off 3. I'd have 2 branches off 3 and 1 off 4. But if I number it backward, or number it from right to left, now I have a branch off 2 and 2 branches off 3. So overall, my numbers are smaller. I have 1 branch that contains 2 carbons, and I have 2 branches that contain 1 carbon. I'm going to write a very long one, then I'm going to show you how to simplify it. So we have 3 ethyl, 2 methyl, 3 methyl, pentane. Now, you think there's a way that I could shorten that up a little bit? What's a prefix that I could use for 2 things? Yep. Okay. Not quite. I'm thinking about a prefix outside of what we've talked about before that can give you 2. That means 2. The proper name for this is 3 ethyl, 2, 3 dimethyl pentane. Di meaning 2, tri meaning 3. Okay. Tetra meaning 4 if we get to it. Okay. Again, the order, the 3 is out here because it's the ethyl branch. Ethyl comes before methyl. Don't worry about the di part of this. It's just the branch name. This one here, doesn't really matter which way I number it. I will number it this direction. 1, 2, 3, 4, 5, 6, 7. The parent chain is heptane. I have 2 branches that contain 2 carbons. So we are going to go 3, 4 diethyl. Di meaning there's 2 branches, 2 ethyl branches coming off the 3rd and the 4th carbon. And then I have a 4 methyl branch. So off the 4th carbon, I have a branch containing 1 carbon. 3, 4 diethyl, 4 methyl. I use dashes. I think the proper is, or I often use dashes. I think the proper is commas, but don't quote me on that. I deliberately made this one weird. If I start here, and there's supposed to be a tick off of here, 1, 2, 3, 4, 5, 6, 7, 8. If I go that way in a straight line, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I go that way. Okay. So again, I'm going to have to number this chain of carbons because my longest chain is 9. And I'm going to number it from that side, and I'm going to talk to you why in a second. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's the reason why I choose to number it that way. The first branch I run into here is off of my second carbon. If I number 1 up here, the first branch that I run into is off of my third, or off my fourth carbon. 1, 2, 3, 4. Okay? So that's the reason, again, why I named it from right to left. So, nonane is my parent chain. I have 2 methyl branches. I have 2 ethyl branches. My ethyl branches come off 4 and 6. 4, 6 diethyl. And then off of 2 and 6, 2, 6 dimethyl. Did not say this was a spoken language. It communicates better written. And it is meant to communicate written. You're not talking with a colleague about this using names. You're gonna, here, this is what I'm talking about. Here's the chart, here's the diagram, here's the structural diagram, here's the formula, etc. Going backwards, drawing it, it's the same basic idea. We have our compounds, we have our parent chains. Our numbers give us what where our branches come off of, and our prefixes tell me how many in each branch. So 3-methylhexane. Hexane is 6. So I draw a carbon chain of 6 carbons. 3-methyl, so off my third carbon, I have a branch containing 1 carbon. Now I go back and I add all my hydrogens in. Sean, you're going to be the one that doesn't do this. You need to indicate all the hydrogens. So everything has to have 4 bonds off of it. Rory would be the next one to do it. Draw the parent chain and then deal with the branches. Parent chain is oct. 1, 2, 3, 4, 5, 8. 3, 4, 5, 6, 7, 8. I've decided to draw this one as a line diagram. Same thing. This is the one that's lazy people need to draw. Off the second and fourth carbons, I have a branch containing 1 carbon. So off the second, there's a branch containing 1 carbon. Off the fourth, there's a branch containing 1 carbon. I don't care if you point it up or down. That's when you start to talk about cis and trans compounds. Also off the 4th carbon. So I started numbering over here. I have a propyl branch. How many carbons in a propyl branch are there? 3. So 1, 2, 3. There is a line structural diagram for 2,4-dimethyl 4-propyl octane. It does, it seems like it's complicated for a lot of us. But if you break it down to like, okay, parent chain, branch off of which carbon? Branch off of which carbon? You have a bit of reading to do, and I'll just grab the assignment. The assignment will not be due till Tuesday. Here's that.